All right, for this next section, I'm going to go over Lightning and a whole bunch of other things, but I want to open it up with an example. Let's imagine you're at some type of Bitcoin meetup, and you really want to do an exchange and sell some crypto, and you want to sell it peer to peer, and let's say you're going to sell like, I don't know, $9,999. Not sure why you would pick that amount. Hint, hint, that's the max you can deposit into your account without having the bank flag it to the IRS. But regardless, let's say you have $10,000 in Bitcoin and you want to make a trade with someone, right? And they bring $10,000. That's a lot of money, okay? And the fact that it takes 10 minutes, like, even if you did that and you're in a safe environment and there's people around and you count the money, like, usually you're ready just to go. Do you want to sit there for 10 minutes? Like, that is awkward. So now we come into, like, how do we do quicker Bitcoin transactions? Is there other ways to do it besides waiting the full 10 minutes? And then you take into the fact that you're generally going to want 3 to 6 confirmations. That means at least 30 to 60 minutes. That is a very long time. Of course, remember that 10 minutes is an average. If we look at this block explorer here, you'll see they have a column for TTM, time to mine. And it tells you how long the block actually took. So you can see this block took 2 minutes and 38 seconds. Next one, 22 minutes. Almost 28 minutes. 16 seconds. 5.5 minutes. 3 minutes. 17 minutes. Almost 22 minutes. 47 seconds. A minute 46 seconds. Like, what the heck is going on? Like, either it's almost double or triple 10 minutes, or it's 10 times less than 10 minutes or more. That's only 16 seconds. That's closer to 40 times less. This thing is all over the place. Let's go to the next page of blocks. 16, 6, 8, 20, 12. Okay, let's go to the next plate. All right, finally, there's something within the 10-minute range. But you see the blocks are all over the place. And, of course, the reason for that, as we discussed earlier in the video, is remember, we're essentially just guessing, and we're approaching an average. So the key is, on average, when we average in all these times, they're going to end up being just about 10 minutes. But when you look into a micro level, it could be anywhere. So the point is that, yeah, you could do a transaction to get lucky and boom, get it right into a block and it takes 20 seconds. Or I think, look at this block. When I was doing this and making slides, here's a block that took 1 hour and 50 minutes. Okay, knowing Murphy's Law and me, this would be the block that I was waiting on, if I ever did a meetup. So is there a better way? Well, that's the Lightning Network. The Lightning Network, we can do this securely on Bitcoin, using Bitcoin, and we could do it in 1 second. Now, how the heck is that possible? Well, I'm about to go into it. Let's go into how the Lightning Network works. So many people get confused about the Lightning Network. What is the Lightning Network? Does the Lightning Network, doesn't have its own token? Like, how can you suddenly make the Bitcoin network, which is really slow, then move really fast? How does that even work? And it's actually a really clever, cool trick, really. So the first thing you need to understand is a multi-signature address. So if you see here, we have Bob's public key. Now, normally, when you pay someone, it's just the address is just a hash of that public key, along with some formatting and whatnot. But it's just a public key. In the case with a multi-sig, let's say we want to have Alice's public key and Bob's public key. This is the actual code. All right, you put a 2. Then you have a key, and then a 2. So it's a 2 of 2. So you need both signatures, Bob's and Alice, for these public keys. And then the command on the Bitcoin is check multisig. And of course, this has to be true in order for the Bitcoin to be released. Here is that data, all written out in hex. It's very long. And then, of course, you hash it, 256. This is it written in hex. Then you hash it again, because you hash it twice for primarily space savings. You use another hash called RIPEMD. And instead of 256 bits, ones and zeros, it's only 160. And then you go ahead and format it into an address. So, in other words, this address represents this piece of code. So in order to spend from a multi-sig, you have to fulfill this condition and have two signatures, both from Alice's signature and Bob's signature, in order to spend the funds. That's what a multi-signature is. So with that understanding in mind, that is kind of the basis of Bitcoin transaction. So let's say Alice is going to meet up with Bob. So she goes ahead and she puts $10,000 of her Bitcoin to this address, right? Because Bob gave her his public key. And she makes a multi-sig address. So this is a 2 of 2 multi-signature address that the only way it can be accessed is if her and Bob both sign, all right? She does this ahead of time before the meetup. It goes ahead, gets confirmed on the blockchain. It's got 10 confirmations before her and Bob meet up. Now they go ahead and go to exchange money, all right? She goes ahead and checks out the money, uses her little marker, confirms nothing's counterfeit. She's good. So what happens? She goes ahead and takes her Lightning wallet, and she constructs a spending transaction, sending the $10,000 over to his address. And she goes ahead and gives it to Bob and sends it and signs it with her signature. Well, Bob is pretty much good as gold. All Bob has to do is add his signature, and now he has access to all the funds. So he basically has a check, right, that has an account at the bank where only both of them can have to sign it to get access to the account. So this check is basically as good as gold. He just hasn't submitted it. I mean, that's the whole point, is he has a transaction, right? Normally he would have to wait at least 10 minutes and do the whole multiple confirmations. But now he doesn't have to. As soon as he gets this transaction and as soon as it's signed, he knows with certainty that this money is his, because he knows that the Bitcoin bank, right, the network, will approve it, because all it needs to be approved is to have both of their signatures, and he can verify that all this is true and that he has all the information needed. So it's basically a golden check. It's a check that'll never bounce. That's essentially what the Lightning Network is. Now you can understand immediately why there's no Bitcoin coin, and why it's not like a lot of these other altcoins where they have a whole separate network, like a whole separate chain with a whole separate coin and all this complexities. With the Lightning Network, it literally is just a transaction, and you're just holding it. You're basically withholding it from going to the blockchain until you're ready. In this case, maybe Bob will do it on his way home, because this is like an all or nothing. But the point is that the instant it's created and the instant he gets it with Alice's signature, he's good as gold. But there's a problem, all right? What do you think the problem is with this situation? This simple example may be a little bit too simple when explaining it. The problem is she don't know Bob. He's a stranger. Okay, she just put $10,000 of her Bitcoin and locked it into an address that he is co-control over. What happens if Bob ghosts her? I mean, I know none of you have ever had anyone ghost you on Craigslist or OfferUp or a Facebook marketplace. No one ever just disappears after you just about to close a deal. But if that ever happens to you, what if this happened? Alice would have lost her money. All right, this is what's called a token burn. All right, I mean, you've heard of tokens burning. When you burn a token, you send it to an address that no one has the keys to. In this case, she sent her money willingly to an address that she only has half of the control of. As soon as Bob disappeared, that money's gone. Until she can find him and get him to sign off on the transaction, she is SOL. Like, this is a really bad idea. That's why you got to be very careful with these type of addresses. Most people that do 2 of 2s, they have both of the keys. Remember, this address represents this, and she can never fill it because Bob's key is gone. So that's probably not going to work. So let's start over. All right, let's do the example again, but let's try it a different way. Okay, so Alice is still going to do this transaction, same way. But this time, she's not going to send it to the blockchain yet. She's going to create not a spending transaction, she's call it a commitment transaction, where she sends all the funds to who? To herself. She's basically doing a refund transaction. And then she's giving it to Bob, and she's like, Bob, I need you to sign this, all right? I signed it. I need you to sign it. And Bob, sure, he signs it. Now, why does he sign it? Because they haven't exchanged anything yet, all right? This is Alice's money. So Bob is essentially agreeing that Alice can have her own money back, And this is like before they meet up. So he's not even worried. He signs this. Now, once he signs this, now Alice will send this transaction to the Bitcoin blockchain and get it verified. Why would she do that? Because she knows that she can get her money back. If Bob disappears, she's not screwed. All she has to do is publish this to the blockchain, and it'll send the money back to herself. So that's step number one. So now what about the trade? All right. So this is Alice's check. So now she meets up with Bob. She counts the money. It looks good. So she creates the transaction. She creates a new transaction. So it's effectively the same as, you know what? I'm going to rip up this check. I'm going to tear it up, and I'm going to write a new check. And this new check is going to be addressed to Bob. And then I'm going to sign it and give it to Bob. And so just like before, Bob's like, all right, cool. I got your signature. All right, I know I can sign it. And this is going to send the money to me. So I'm good to go. Right? Well, not really. Because as you can imagine, the rip check analogy really doesn't work. Because this isn't a paper check. How would you know that the other person ripped it up or deleted it? Be like, oh, sure, yeah, I hit delete. No. There's no way Bob can know that Alice deleted it. So really, it's a race, because now there's two transactions. And they're both perfectly valid. One sending the money to Alice and one sending the money to Bob. So nobody is really secure yet. Bob is not secure until what? He gets this put on the blockchain. And he's got to make sure it gets there before Alice's does. Otherwise, he's SOL. So this whole setup doesn't work. We need a way to rip up the check, so to speak. So let's do it one last time. All right, but this time we'll do it for real. So again, we're going to start off the same. We're still putting the funds in the 2-2 multi-signature. All right, and we're still doing the refund transaction. All right, but we're making a change. Instead of sending the $10,000 to Alice's address, we send it to a different address. All right? It's called an RSMC. It stands for a Revocable Sequence Maturity Contract. Okay, what is that? It's basically a smart contract. Now, yes, I know many of you heard Bitcoin doesn't have smart contracts. That's Ethereum and Cardano and Polygon and Avalanche and all these other ones. Bitcoin is just dumb. No. Don't get me wrong. Bitcoin is not nearly, it doesn't come anywhere near these other chains when it comes to pure intelligence, but it's not dumb. And a smart contract, I would more aptly call it like a smart-ish contract. Really it's a script. Bitcoin can be fully scripted. What it can't be is programmed in a redundant way where you have loopable code, but that's beside the point. And you're about to see how simple this smart contract really is. So you saw previously a multisig look like this. 2, 2, check multisig. Well, now let's take a look at the smart contract. It basically is in an if-else statement. You have two conditions. One, if, and we have the same thing, 2 of 2 multisig, but instead of Alice's pub key and Bob's pub key, we have Alice's revocation key and Bob's revocation key. Well, what keys are these? Well, when they do this, and when they're setting up their wallets, are creating these transactions and going through the process of signing them, they also create their own revocation keys. Alice creates a revocation key, which is basically just like a public key. It's their own personal public key that she has the private key to. And Bob does the same thing. And they agree that this is a spending condition, that whoever has both of these can actually get paid. In this case, Bob can get paid. Now, neither of them have this at this point. So we can just ignore this for the time being. But it's just a possible condition. So we'll get to this. The else is where we want to get, and that's the refund, which you see Alice is going to get paid just like before, but we have this wait for 24 hours. Well, why would you need to wait for 24 hours? Why would we make Alice wait 24 hours? You know, that's kind of weird. And that's called a time lock. That's a very important feature that's built into Bitcoin script logic. In this case, it could literally look like this: 144 check sequence verify. 144 blocks is basically a day, 24 hours. But how? How can we make Alice wait? Like, how does that even work? Well, it works quite simply because if Alice wanted to fulfill this part of the smart contract, right? So she puts it to the blockchain. They're all good, but then Bob ghosts her. Bob's like, I'm out. Alice is like, right, no big deal. I'm going to go ahead and get my money back. Well, the first thing she does is she publishes this to the blockchain. Because as soon as she publishes this to the blockchain, because this is both signed, let's say she publishes that block 810.123 at 12/2/22 at 8 a.m. All right. So now basically the clock has started. The clock starts as soon as this transaction gets on the blockchain. Now she has to create another transaction to spend it, and this is where she sends all the money to herself. Now, how does she spend it? She has to fulfill the contract. She can't fulfill the first condition, but the second condition, she just needs to wait. So let's say she's impatient. She's like, you know what, screw this. I'm going to sign it. I'm going to send it to the blockchain at 10 a.m. So she only waits 2 hours. Well, what happens? This gets to the mempool, and it probably gets rejected just by the memory pool, because the memory pool can read this. But even if the memory pool couldn't read this, as soon as it tried to get verified, it would fail. It would fail because the code says, hey, has it been at least 24 hours since this time? No, it hasn't, so it's rejected. The only way this is going to go through is if it's been at least a day and she waited 24 hours. So the next question remains is why? Why would we make Alice wait 24 hours? What's the purpose of that? And you'll see that very quickly for when I finish the next part. And the next part is, let's go ahead and do the final transaction. So let's say Bob doesn't disappear. All right, he shows up. They look at the money. They exchange the money. Alice checks out the money, and she decides, all right, I'm going to pay you. So she creates her commitment transaction, right? And she's going to pay the $10,000 over to Bob's address. She goes ahead and signs it. Bob is like, all right, Oh, sorry. Bob is like, you know what? Your signature isn't enough. I need to get your revocation key as well. Alice is like, oh, sorry, my bad. Alice goes ahead and gets her revocation key. Now that Bob has her signature and the revocation key, now he knows he's seriously good to go. Now, why does he know that? Because he has all the information he needs to spend from the other condition. Remember, Bob wants to get paid. He just needs to he needs to be able to provide the signatures for both the revocation keys. So he needs this information from Alice. Once he has that, the deal is essentially complete in his mind. Now, what about the previous condition? Remember, the whole thing we wanted to address is the ripping up of checks. What happens if Bob's on his way home and Alice is like, oh, screw this. I'm going to try to steal the money behind his back. And she decides to be devious and post this commitment transaction. Well, we already went over that. She'll go ahead and publish this to the blockchain. As soon as she does, what happens? The clock starts ticking. Now, his wallet is constantly watching the blockchain. While Bob's driving, his wallet is every single block. It checks because it's always checking to make sure no one's trying to break the rules. So Bob can see what's going on. So as soon as this posts to the blockchain, Bob's wallet sees that and it's like, oh, okay, you want to try to steal funds? All right, well, no big deal. I'll go ahead and create my own spending transaction, and I'll go ahead and send all the money to my address. And because I have the revocation key and I have her key, because remember, he has both revocation keys. So the difference here is that he doesn't have to wait. Bob does not have to wait. Alice does. So this 24 hours is basically an open window to give the other party a chance to reclaim their funds. So now he gets paid. All right. So this is a very oversimplified, but this is essentially you understand how the Lightning Network currently works. Now it's going to be upgraded with Taproot and some other things called point time locks or point locked contracts where we no longer have to use time. But currently this is how it's implemented. This is our ripping up of the check because technically you can't revoke anything. All you can do is disincentivize bad actions, So Alice would never do this in real life because she knows it would never work. And that is a revocable sequence maturity contract, which now it makes sense because it's something you do in sequence, maturity over time. This allows you to revoke it, revocable sequence maturity contract. But that still begs the question of, first I'll give you a more apt example because this is kind of strange because you're like, normally you don't open a Lightning channel and to do one big payment. Normally the Lightning channel operates a lot more like a tab, So Alice opens a tab with Bob and all the for $100, and then she buys some drink for $10. So you can see on Bob's side, he's got $10, she's got $90. So they're going to have an updated balance that goes back and forth. But they're still going to follow this process over and over where once, because initially she's going to have a refund transaction. Once she pays Bob, she's got to be able to rip up the check. So she's going to use that revocable sequence maturity contract to make sure, so Bob is assured that she can't go back and steal anything, And then she can see, and every time she spends $10, $10, $10, and the balance change, you're able to revoke the previous transactions doing exactly what we went over in the previous slide. And you see here, the consequences are much more severe because at this point, Alice has $40, right? And she's paid Bob $60. If she tries to cheat Bob, what happens is Bob will end up going and publishing the transaction where he gets paid back everything, so he can take the full amount. That's a whole separate thing, but I just wanted to point that out. So that's really great, this whole payment channel, but obviously it still involves some locking up of your Bitcoin. Like this is $100. When Alice opens up a payment channel with Bob, she's locked up $100 of her Bitcoin in a multi-signature to do all this. That's $100 she doesn't have available. All right, and she may have more than one payment channel. Let's say she does this with her best friend, Kate. Okay, that's great. But are you going to do this with everyone? Like every time you want to pay someone, you got to lock up funds? Like that doesn't make any sense. What happens if she goes to the gas station and just wants to get gas? Like she has to open a payment channel with the gas station? Like this doesn't seem very feasible. And luckily, it is very feasible because she doesn't need to. Because you have a network effect. So Kate also has a payment channel with her friend Gordon. Gordon may have a payment channel with the hardware store. The hardware store's got a payment channel with Paul and Bob. They're great, they're clients or whatever. And Paul's got a payment channel with the Shell gas station. So whatever, 6 degrees of Kevin Bacon, we can route that payment through all these people in order to get to Shell. So she no longer needs to open payment channels with everyone. All she needs is a connection to the network, but she's got 2. And from their connection and their connections and their connections, she can pay other people within this network of connections. So it would work like this. She'd send a payment to Kate. Kate would send it to Gordon, hardware store, Paul, all the way to Shell. Now, how does that work? All right. Well, we're going to have a new type of contract. So first is Shell's going to come up with a payment secret. All right. Alice is going to say, hey, I want to pay you $20. So they're going to come up with a payment secret. Again, most basically like a public key. All right. And then it's going to scramble it. It's going to hash it, And then it's going to share that hash secret with Alice. So Alice has this scrambled secret. Now what Alice can do with this scrambled secret is she can now create, through her payment channel with Kate, basically say the following, like, hey, Kate, here's our balance right now. We're 50-50, all right? What would you do if, yeah, normally this is Alice's 50s in the revocable sequence maturity contract to protect Kate, right? And here's the RSMC. What would you do if I wanted to pay $20 to Shell? So Alice could deduct $20 from her balance to the revocable sequence maturity contract, right? And then offer to pay Kate an extra $20, but do it in a separate address. But this address isn't addressed to Kate, it's actually to a new smart contract called a hash time lock contract, an HTLC. And this contract's even simpler. It just says, look, if you want to get paid, you just need to get the payment secret. That's all you need. Because within this piece of code is the scrambled secret. So basically, you need to get the secret such that if I hash it, it'll come out exactly equal to this scrambled hash secret. So all you need is the payment secret. That's pretty much it. Now, normally it would look something like this, because why would Kate even agree to do this? Well, because she's going to get paid. So let's say she's going to get paid a penny. Well, if she was going to get paid a penny, Alice would have to come out and pay the fee on her cut. So she takes out 4 cents, and now she's like, all right, Kate, I'm going to pay you $20.04 if you go ahead and forward this along. All right? And Kate has every opportunity and unction to pass it along, because why not? She's going to make free money. So basically, Kate makes the same exact deal and contract with Gordon, with their thing. She's like, hey, Gordon, I'll pay you $20.03, right, if you go ahead and pass this along. And Gordon doesn't mind doing it and putting up his money, because he knows he'll get paid as long as he gets the secret. So he does the same thing with the hardware store. Hey, hardware store, I'll pay you $20.02 if you can get the payment secret. And the hardware store says, Paul, hey, I'll pay you $20.01 if you can get the payment secret. And Paul's like, hey, Chevron, I'll give you $20 if you give me the secret. Chevron's perfectly happy because they want the $20. So they take the $20 and they give Paul the payment secret. As soon as Paul gets the payment secret, he publishes it on the net to get paid, and he gets 1 penny. I mean, obviously, he got paid $20.01, and he paid $20, so he netted a penny. But he got paid a penny for really doing nothing, and everyone follows this, because as soon as this goes on the blockchain, everyone's looking, everyone can see the payment secret. So the hardware store is like, oh, shoot, okay, well, now I'm going to get paid. So he goes ahead and collects his $20.02. Gordon collects his $20.03. Again, everyone's netting a penny, because he paid out $20.02 to the hardware store, and Kate paid him $20.03. And then Kate, she nets her penny. She gives the payment secret to Alice, and she gets paid by Alice. So Alice was able to route through, and this is all done privately using something called Onion Routed Network, which we'll go over. But she was able to just have everyone pass it along in a trusted way, simply by doing this operation of sharing a payment secret. Now, in addition, there's a little bit extra complexity, because we also put time conditions, because we don't want everyone doing it at one time. We want it to unwind in order backwards, because if everyone tried to do it, it would screw things up. So there's another time lock thing that comes into play here. But for the sake of simplicity, this is pretty much the gist of it. And that's it. That is like the gist and the heart of the Bitcoin Lightning Network. These connections are literally I don't even know now. I have to look it back up, but it's in the hundreds of thousands. There's just connections. Basically, as long as you open a payment channel on the Bitcoin network, anyone else that has a payment channel on the network is going to be able to find their way through it to get a payment to you. And people are incentivized to do exactly what I showed you, because it's all done in a trustless manner, where there's no way that you can get screwed. There's no way that anyone can be like, oh, man, I just lost my money. All you have to do is pass it along. All this takes fractions of a second. And if you do that, then you'll make a little money, make a few Satoshis, and you can actually earn money. And that's it for the Lightning Network.